mentioning, we have these in the 2 key concept boxes here are the identities that we have already learned last semester. Okay, so these 6 are the reciprocal identities. Okay, hopefully you know by now which identities are reciprocals of each other. These 2 are the quotient identities. Quotients divide, so these are the 2 that are the division of 2 different trig functions. So tangent is sine over cosine, and cotangent is cosine over sine. And then, as I was mentioning, right before semester exam time in December, we learned the Pythagorean identities, okay? There were 3 Pythagorean identities, but we did talk about they can be rearranged as long as you follow algebraic rules. So for instance, I could subtract cosine squared theta to the other side, couldn't I? If I put it on the other side, it needs to change signs. So sine squared theta equals 1 minus cosine squared theta is also a Pythagorean identity. It's just a variation of this first one. Do y'all remember that? So these are the way that these 3 are typically seen, but there are alternate variations. You can rearrange them as long as you follow the correct algebraic rules. So what we're going to do today with these identities that we already know, so we're kind of reviewing those, is we are going to do what is called verifying. So we are going to verify these trig identities. Verifying, I don't know why that's highlighted. There we go. Verifying is simply proving that one side of an equation is equal to the other side. Now, this is different than solving. When we solve equations, we get the variable by itself and move everything to the other side. We're trying to get a numeric answer when we're solving. That's not what verifying is. When we're verifying or proving an equation, we only work one side of it. We don't move things across the equal sign. We pick typically the more complicated side to work, and we just manipulate it using trig identities and algebraic operations like factoring or simplifying or reducing or multiplying by conjugates or squaring, foiling, all sorts of algebraic operations that you should know how to do. We use those and these trig identities to manipulate and rearrange one side of the equation until it matches the other. Once we do that, we have proved, we have verified that it is indeed true. Does that make sense? All right. These aren't like formal proofs. You probably did some formal proofs in geometry. Do y'all remember that? Yes, no, maybe so. Like where you had like a 2-column proof on one side, like you showed each individual step, and on the right side you had to say like the rule you were using. Some people remember. So you can kind of think of it like that, but it's not a formal proof. We are proving that these are equal, but we're not setting it up like a formal proof. But I am, for the sake of our notes, as we do each step, I am going to like make little side notes of what rule I'm using or what identity I'm using. You don't have to do that when you're showing your work and doing practice problems, but it's not a bad idea until you really get the hang of it. There is an Alex practice assignment that is active, and it's due on Thursday before midnight. And there is a type of problem in Alex that does make you do it more like a formal proof. It's got like a drop-down menu of like what identity or rule you're using. And so you can only do like one little step at a time, and then you select in the drop-down menu what it is you did. But besides within that particular type of problem in Alex, I'm not going to make you write what you're using every single step of the way. Okay, so for this first one, we want to prove that cosine theta times tangent theta times cosecant theta equals 1. Okay, so we can prove that by working, I would say the left side's the more complicated side. Okay, we're going to work the left side until we get it to 1. Okay, we're going to verify this trig identity or using trig identities. So one strategy is that you can use when you're doing problems like this, when you're asked to verify, is to change all of your trig terms to put them in terms of sine or cosine, if possible, because sometimes that will let things reduce or simplify nicely. Okay, so cosine theta, obviously already in terms of it cosine. Okay, is there something we could use? Is there a trig identity that we could replace tangent with that would put it in terms of sine or cosine? Look at those in those key concept boxes above. Like, so this one puts tangent squared and secant squared together. That wouldn't be helpful, and we couldn't do it anyway. Tangent to cotangent, but what about over here? Tangent is sine over cosine, right? So I could replace tangent with sine over cosine because those are equivalent. So that's what I'm going to do. I'm going to replace tangent with sine over cosine. Okay, and like I said, I'm going to make little side notes as we go. This is the quotient identity. Okay, so I'm using quotient identity there. Cosine is still here. We didn't replace it. Okay, now, is there something I could replace cosecant with to put it in terms of sine or cosine? What could I do? What could I substitute in for that? Yeah, I could use the reciprocal identity, which says cosecant is equivalent to 1 over sine. So I used quotient ID here, reciprocal ID here. Now, do you notice anything we can do just algebraically? Yeah, there's going to be some terms that reduce, aren't there? Because we have common factors in the numerator and the denominator. Okay, these are all being multiplied. There's no pluses or minuses here. So my numerator is cosine times sine times 1, or just cosine times sine. And my denominator is just cosine times sine. And everything reduces. The cosines reduce, the sines reduce. I'm left with just 1. 1 times 1 times 1 is simply 1. So I have verified that this side breaks down, simplifies to 1, which is what I was trying to prove. So I'll make a note here. I did reduce. Yes. Sure. Yes.
Like, why did, for that example, why did you put the reciprocal for cosecant? Why did you only do tangent and cosecant?
Cosine was already in terms of cosine. So the strategy I was showing y'all for this one is to put everything in terms of sine and cosine, and that already was cosine, so I didn't need to change it. Strategy doesn't work every time, all of the time. What you're going to come to notice as we do more of these is these are kind of like puzzles. Sometimes you might see some obvious starting point. Sometimes you may try something and it's not working and you got to start over and try a different way. It's like flipping your puzzle piece around, trying to make it fit until it does. So it's not as straightforward as solving like an algebraic equation might be. There's multiple ways sometimes to go about it. And sometimes it's more obvious than other times. Okay, there's definitely going to be some harder ones. What you may realize once we do a few more of these together and you try the check for understanding is I don't think that the trig is really going to be much of an issue for y'all because you have the identities here. You're going to get to a point where you know these like the back of your hand. You're not going to have to refer to this. but it's going to be recalling all of your algebraic operations, all of your algebra skills. That's actually where people tend to mess up more than with the trig substitutions, with the identities. Okay. So, I mean, we're going to use all those old algebra skills mixed in with these, as well as these trig identities. So here in example 2, would you say the left or the right's the more complicated side? I would definitely say the left. Now, this is one, everything's already in terms of sine and cosine. I can't really use that strategy as a starting point because it's already done. Okay, so I have to look at it a little closer. I know right now I've got 2 terms with a subtraction in between, and I'm trying to prove that it's equal to this single term over here, the single trig function. So I know I'm going to have to get rid of that somehow. So there's going to be some sort of substitution replacing terms that are being added or subtracted with a single term. Okay. And the fact that I see lots of squares, that should make me think of my Pythagorean identities, right? Now, I don't see any right away. There's no substitution I can immediately make. Okay. But is there some algebra I could do to get us started? Looking at the left side of this equation, what do you notice about both of these terms? They're both squared, yes, but they both have something more specific that can be factored out. They have a GCF, a greatest common factor. So that's what I'm going to start with. I'm going to take that cosine squared out of both of those. So I'll make a note of what I'm doing. I'm doing greatest common factor. That's the step I'm doing first. I'm doing GCF. So if I take out the cosine squared, what am I left with? What negative sine squared? Am I missing something if I just write negative sine squared? 1 minus sine squared. A lot of people tend to forget this 1 has to be here. When you are factoring, you're literally dividing that term out. If I take cosine squared and I divide by cosine squared, it's not 0. It's not gone. It just reduces to a 1. So you cannot forget that 1. So it's 1 in place of this minus, and then here the cosine squared divided by the cosine squared reduces to a 1, but it's being multiplied by sine squared. So 1 minus sine squared is what's left. So now, does that ring a bell or look like anything? Yeah, this is going to be a version of one of these Pythagorean identities. Which one? Yeah, if I rearrange this so that it's 1 minus sine squared, what's it equivalent to? If I subtract that sine squared to the other side, what am I left with? Cosine squared, right? If I move the sine squared over here, the right side becomes this 1 minus sine squared, which would be equivalent to just the cosine squared. So I can make that substitution. 1 minus sine squared is equivalent to cosine squared. And I've still got the cosine squared out front. This right here that I'm doing is a Pythagorean identity. I'm going to go ahead and color code up here. I'll use the same colors, all of the notes. I'll do all of the reciprocal identities in pink, Pythagorean in yellow, and I'll do all the quotient identities in blue. So we can keep them straight. All right, now what? Cosine squared times cosine squared? Yeah, I just simplify this. I multiply that. It's like x squared times x squared would be x to the 4th. So cosine squared times cosine squared is cosine to the 4th, which is what I was trying to prove over here, isn't it? So the left side does indeed equal the right side. So that is verified. So far, so good? Okay. So that only had one identity that I used in it. The other steps were just algebra. It was factoring and multiplying like base terms to a power that were raised to powers. All right, now this one, example 3 and 4 are exactly the same. It's the same problem, but I'm going to try it one way, and then we're going to try an alternate way. We're going to try a different method, okay? Because I want to show you that there is not always just one way to prove or verify these. In this particular one, some people might interpret the left side to be the more complex side. Some people might say the right side is, because you have those trig functions being added together, okay, instead of as a single term. Some people think the fraction's more complicated. So I'm going to show you working the left side and working the right side so you can see how we can prove it either way. Do y'all have a preference on which one we start with? Right? Okay, so I'm going to do the right side on the right side. So I'm going to use example 4 to work the right side of this. Oh, why that is highlighted. Okay. So I'm going to work the right side over here. So I can't factor. There's nothing to reduce. So what's a strategy that I've told you you can try sometimes? If you don't know how to get started on this right side, I know that eventually I want them as sine and cosine over here, right? So maybe that's a good strategy, is to rewrite these in terms of sine and cosine, like we did on number 1. Okay, so what would cosecant be rewritten as? And what would cotangent be rewritten as? So this one is the quotient ID. And this one is the reciprocal ID. So let me highlight and show what I did there. I already forgot what color I used. Blue was quotient. Okay. So I made this substitution here. And this substitution here. All right, now, what can I do? I have 2 fractions I'm trying to add. What do you have to add fractions? And do I have a common denominator? I already do. So I can already go ahead and combine those, can't I? Okay, so my next step is just some algebra. I'm just going to combine the terms. I'm going to add the fractions. So my numerator is going to become 1 plus cosine, and my denominator is just sine. We just add the fractions. All right. I look somewhat similar to what the left side's supposed to be. Like I've got a 1 and a sine and a cosine, but not exactly where they should be, right? So I'm not done. Any ideas on what I could possibly do from here? An algebraic step, because there's no identity right now that I can use. But there's an algebraic step that you probably haven't done in a long time that you could use here. Any ideas? Not by the reciprocal, but by the What do you mean when you say that? Like, tell me what you would actually multiply by. No, because that would just reduce them. And you can't just pick things to multiply by that you wouldn't multiply both the numerator and the denominator by, because you'd be changing the value. Remember, we can't move things across the equal. So we're not changing anything on the left. We're only working the right side. Okay, that's a good thought. Any other ideas? So if I multiplied by the like just multiply by sign to the numerator and the denominator.
Yeah.
So I could do that, which would give me sine squared. But in my numerator, it wouldn't really get me to a point where I could do anything, right? So I'm not going to say we couldn't do that. That actually may eventually work itself out, but it might be a longer path. Any other ideas? No? Okay, well, we're going to use Josie's then if nobody else has any ideas. We'll do it. We'll see if it eventually works out. So she said, let's try multiplying by sine. Now, if you do that to the denominator, you have to do it to the numerator because we're actually just then multiplying by 1, right? Because anything over itself is just 1. Y'all agree? So you'll see how we can, if we want to multiply by something, we can, as long as we do it to both the numerator and the denominator. Cool? All right, so if I do that, then I'm going to leave the numerator factored. I'm not going to distribute that sign in. But this would become sine squared, wouldn't it? Y'all agree? Okay. Now, why would you want to get it to sine squared? What was your thought? What could we do from here now? Well, if I do that, then I'm just right back to where I started on the previous step. Right? If I reduce a sign here and here, that's just getting rid of what I did to get here. Did you have an idea when you said multiply by sine, Josie, to make it sine squared? Why would sine squared be helpful? Look at your identities. Is sine squared somewhere in one of your identities? In this one right here. So what would sine squared be equivalent to? 1 minus cosine squared, right? So I could try making that substitution. So I could say, okay, I'm going to replace that sine squared with 1 minus cosine squared. I'm making that substitution right there. That's a Pythagorean ID. Now, it's got a somewhat similar expression here in the numerator and denominator, but not exactly the same to where I could just cancel them. But what is this denominator now? Ignore the numerator. Just what type of expression is this? Is it a sum, difference, product, or quotient? If this is a minus here, what do we call this? How's that? You're on the right track, Cody. Is this a sum or a difference? Difference of squares, because 1 is a perfect square and cosine squared is a perfect square, right? So I could factor this. And then one of my factors would be this one that's in the numerator, wouldn't it? So if I factor my denominator using difference of squares, I'm running out of room, so I'm not going to rewrite the numerator. I'm just going to factor the denominator right underneath it. But difference of squares, I'll write what I'm doing. Difference of two squares, factoring. I factor the first term. The square root is 1, right? And what's the square root of cosine squared? Just cosine, right? And then what do I do? What's the difference in these two? I do one positive and one negative. So one plus and one minus. So this is factoring that Pythagorean identity, which then allows me to reduce the cosine plus 1, because that's in both the numerator and the denominator, right? And what am I left with? Sine over 1 minus cosine. Is that what I was trying to get it to? Yeah. So that did eventually work. What Josie said to try. Then Cody helped us figure out that we could do difference of squares. Good job, guys. So if I had more room, I would go ahead and write that out a little neater, but I ran out of space. Does it make sense though, what we did? So that was one way to do it. That was not the only way to do it. When we try the other side, I think I'm going to refresh your memory on another algebraic step that you could use, that we could have done here. You all good with this side? Okay. So let's go back. Let's try working the left side instead. Okay, so if I'm trying to work this, ooh, did not mean to do that. If I'm trying to work this left side to get it to match the right, I know eventually I'm going to have to get rid of this out of a fraction because the right side's not a fraction. But there's not much I could do right now. Like there's nothing to replace or simplify yet, is there? So this is where I'm going to remind you of an algebraic process that you probably haven't done in a while. See if you remember what this is called. So I'm going to make this, I'm going to create a cosine squared by multiplying by 1 plus cosine. Instead of 1, it's already 1 minus cosine. What is that called? Y'all remember? What is 1 plus cosine in comparison to 1 minus cosine? Starts with a C. The conjugate? Does that ring a bell? It's been a while since you've done it. I don't know when the last time you would have done it in Algebra 2 is. Maybe with when you did imaginary numbers. Ringing a bell yet? Been a while. So this is called a conjugate. You just simply changed the sign of the binomial. And the reason that I would want to do that is because when I go to FOIL this out, the middle term is going to cancel because I'll end up with a negative cosine and a positive cosine, right? So when I FOIL that out, my denominator then becomes 1 minus cosine squared, which that's a Pythagorean identity, right? So that's why I would want to do this. Now, just like over here, when we wanted to multiply by something, we had to multiply the numerator by it as well. Same thing applies here. So if I'm going to multiply the denominator by that, I have to multiply the numerator by that. So I'm going to leave it in that factored form. I'm not going to distribute the sign. And I'm going to write this, what I did. I multiplied by the conjugate. Now, that leaves me with a trig identity, the Pythagorean identity in my denominator that I can use, I can replace this with. What is that equivalent to? Sine squared. So I can make that substitution. Nothing's happened to my numerator. Still 1 plus cosine times sine. Okay, but what can I do now? Yeah, so I'm going to write that I used the Pythagorean ID here. Now I'm going to reduce. The sine factor in the numerator and one of the signs in the denominator can reduce. So I'm going to be left with 1 plus cosine over sine. What can I do from there? I know I've got to separate this somehow into two terms. That's what I'm trying to work toward, is two terms being added, right? How can I do, can I separate this since there's two terms in the numerator? Yeah, what is that? What will it become? What do I do? Yeah, if you have addition or subtraction in your numerator, you can separate this out into separate terms. You just keep the same denominator. So the 1 over sine and the cosine over sine can be separated. Now what could I do? Yeah, this is a reciprocal identity for cosecant. It actually equals cosecant. I'm going to be able to substitute that. And cosine over sine, that's a quotient identity. I'm going to be able to substitute that. So 1 over sine is the same as cosecant, and cosine over sine is the same as cotangent. So I can make those substitutions. And is that what I was trying to prove? Cosecant plus cotangent, isn't that what the right side was? Yeah. So I proved it. And that was, I'll write here again, that is quotient identity. And this one is reciprocal identity. So I used multiplying by the conjugate. I used Pythagorean identity. I reduced. This was just algebra, separating the to fractions. I used reciprocal and quotient IDs. This is what I could have done over here at this point when we decided to multiply by sine. Instead of doing that, I could have multiplied by 1 minus cosine. I could have multiplied by this conjugate, and it would have been kind of like the reverse of what I did over here. And that would have worked out as well. Y'all feel okay about those? All right, so there are some check for understandings on the back. Okay, so I went over a few algebra skills, went over some strategies. I want you to try and apply those on these check for understanding questions on the back. There are 7 of them. Okay, some of them are a little longer than others. You can try them on your own. You can talk to a neighbor or work with a partner if you'd like. If you and a neighbor or two are all stuck, you can't figure out where you're supposed to go from a point, you can ask me. Okay, but I want y'all to give it a shot. Actually try and think through it and ask some questions of your neighbors before y'all just come to me for relief, okay? Try and struggle through a few of those. It's a very different concept. A lot of people really dislike this unit because it is like a puzzle and they don't like puzzles. But some people really enjoy it because they do like puzzles. So, but y'all give those check for understanding a shot. And then don't forget that there is an Alex assignment online and it is due Thursday before midnight. Okay. So you have today, tomorrow, and Thursday to work on that Alex assignment. I think it's only 7 questions on the Alex as well. So not too long, but there is that one type that wants you to do it like kind of like a formal proof where you have to do each individual step. So like on example 1 here, where at the same time I did the quotient and the reciprocal ID, you won't be able to do that in that specific type of Alex problem. It'll make you do one at a time. It'll make you do one of them and say what you did, and then you can do the next one and say what you did. Okay, so just be aware of that. All right, that's it for today. You'll work on those check for understanding, and if you finish them, then you can start on the Alex.